Hi, this is Wendy Pin presenting the first lab report about constant velocity. So the purpose of the lab is to observe the motion of an object moving at constant velocity and apply Newton's second law. I used a marker for the lab and it will be denoted as pen later. So basically, we'll apply Newton's second law, and the general formula is F equals ma. And in this lab, the acceleration will be 0 because we focus on the constant velocity motion, which means the net force acting upon the object is also assumed to be 0. And that goes back to Newton's first law as well, which is an object remains at the state it started with if there's no net force, which we will assume that the object will keep moving in the lab, but that will not be the case, as we will discuss later. And then there's the velocity update formula. The final velocity equals the initial velocity plus the acceleration times delta t. But in this case, the final velocity will be assumed to be equal as the initial velocity. And then the position update formula will be used as the final position equals to the initial position plus the average velocity times delta t. And in this slide, the net force, acceleration, velocity, and position are all vectors, which I just didn't put the vector signs on. And then there are some key assumptions in the lab, but will be discussed later, which is there's no air resistance, no friction, no motion in other axis other than the horizontal motion that is mainly track. This is a free body diagram of what force the pen is expected to encounter in constant velocity, and ignoring all the resistant forces. The magnitude of the normal and gravity forces should be equal, so they cancel out as they are pointing to opposite directions. To move the object from stationary state to moving state, we will apply a force toward the right, so there will be an arrow toward right, and that will be where the net force pointing towards to. And in reality, where all the resisting forces do exist, there will be other arrows pointing elsewhere to represent any other forces. In this case, the pen is the system, and everything else, such as the table and air, are the surroundings. This is a snapshot of one of the frame of the video tracker. From the graph on the right, we can see it measures the change in position in the x-axis, which is the horizontal direction in meters, in respect to time in seconds. The red dots are to indicate the center of the pen in each frame. I did it manually, so there will be errors as well. The origin of the axis is set to be the center of the pen at 0 seconds. This is the tracker analysis page. I linearized the graph to let it calculate an average velocity for later use. I also manually fixed the y-intercept of the equation to be 0 because I couldn't click the pointer to be exactly at the origin for tracking the video, so there was a little bit off. Theoretically, the pen should be starting at position 0. The average slope here is approximately the average velocity, even though the pen accelerates at first in order to transfer from a stationary state to moving. But the pen also decelerates due to friction at last. Note that each step in the data collector is 1 over 30 seconds. Taking those data to GlowScript, first setting the initial conditions, the starting position of the pen is approximately 0, and the initial velocity, which is the average velocity of the pen throughout the simulation, is 0.52 meters in the x direction per 1 over 30 seconds. So delta t is set to be 1 over 30 seconds. Since the video is only 2 seconds, the code loops while t is less than 2 seconds. In the loop, the position update formula is used, and it plots out the position versus time graph and updates the time each time it loops over. And then here's the result from GlowScript. This is a graph comparing the computational model I have by implementing code on GlowScript and the actual experimental data I collected through Tracker with the video I captured during lab. Since the pen accelerates at first, as we first pushed out, and the observed graph is slightly higher in position than the model. Same thing over to the tail of the graph. The pen decelerates due to any resisting forces, and so the observed graph is slightly lower than the computational model. And in summary, the possible errors are putting the center of mass not at the exact center of the pen due to manual clicking, the resisting forces, and we did not take motions in other directions into account. And then flipping the axis would not really affect the results. It would just produce a negative slope because the velocity is negative. The magnitude remains the same, and it's not possible to say how many forces there are because we don't really, we can't really know, just because there is no net force. They just cancel out probably.